Hey guys, so this video lecture is just dedicated to integration practice. And what I mean by integration practice, I mean evaluating definite integrals using all the techniques we have gone over so far, ranging from power rule, log rule, trig rules, exponential, use substitution, and the fundamental theorem of calculus. The reason I want to dedicate a couple lectures just to practicing integration is because one, well, you have a gateway exam over it on the 14th of April. It's going to be 10 questions, multiple choice, and it's just going to be evaluating 10 definite integrals. And second, because it's an incredibly important part of calculus, and you'll be expected to know it in pretty much every math class you take on from here on out. And with that, let's just get to practicing. So first up the bat, we want to evaluate the definite integral of 1 over 2x from 1 to e. So let's do this. First up, I just like to pull constants out in front. I don't like dealing with them. Just pull them out in the front, and then you don't have to worry about it until the very end. So I'm going to pull that 1/2 out in front. And now we have to evaluate the integral from 1 to e of 1 over x dx. But if you remember, the integral of 1 over x is just the natural log of the absolute value of x from 1 to e. It is the kind of partner antiderivative formula that goes with the power rule. Remember, the power rule is for all exponents except -1. This is the exponent -1, so we have its own rule, and it is the natural log rule. So from here, now we implement the fundamental theorem of calculus, where we plug in each of these limit points into our antiderivative, take their difference, and then that is our result. So this is the natural log of the absolute value of e minus the natural log of the absolute value of 1. But since e and 1 are both positive numbers, the absolute value of positive numbers itself, this is the natural log of e minus the natural log of 1. And then we get the natural log of e is actually 1, and the natural log of 1 is 0. So it's 1 minus 0 times 1/2, and this is just equal to 1/2. So this is how we're going to tackle this problem. Pull a constant out in front. Recognize that the integral of 1 over x is the natural log of the absolute value of x. We have our limit points 1 to e, and then we just implement the fundamental theorem. Plug in these two endpoints into our antiderivative, take the difference, simplify, and we got our answer 1/2. So that's it for that example. All right, now let's look at integrating a polynomial. This one, we're going to use a couple different rules of integration, and then we're going to use the power rule for integration at the very end, and then wrap it up with the fundamental theorem. So first one, well, we have the integral of a sum. But if you remember from the properties of integrals, the integral of the sum is just the sum of the integrals. So I can pass this integral through the summation. So I can just evaluate the integral of each individual piece. So I can take the integral from 0 to 1 of 3x squared plus 2x plus 1 dx and break it up into the integral from 0 to 1 of 3x squared dx plus the integral of 0 to 1 of 2x dx plus the integral from 0 to 1 of 1 dx. And now I can do this piece by piece. So the first one, well, that's 3x to the 2 plus 1 over 2 plus 1, and we will evaluate it at 0 and 1. As you recall, this notation right here just means, hey, we found the antiderivative, but we still have to do the fundamental step. So it's basically just a reminder that's going to hang along with you until you're ready to deal with that. And the next one, we get 2x to the 1 plus 1 over 2. We evaluate this one from 0 to 1, plus, and the integral of 1 is just x, that is 0, 1. And if you'll remember, we're usually supposed to have constants when we do indefinite integration. However, since we're using the fundamental theorem, we take the difference at the endpoints. The constants will cancel out. So here we don't have to worry about the constants. So that's kind of nice. And now I'm going to simplify this a little more. And in case you're curious, the step I just did before is the power rule for integration. Add 1 to the exponent and divide it by the new exponent. That's what we do when we're trying to integrate x to some power. So this simplifies to 3x cubed over 3 from 0 to 1, and those 3's will cancel out, plus 2x squared over 2, but those 2's will cancel out. We evaluate that 0 to 1, plus x from 0 to 1. Now we actually do the fundamental step, where we take each endpoint, we plug it in the function and take their difference. So this is 1 cubed minus 0 plus 1 squared plus 0, and then plus 1 minus 0. Apologize, that's supposed to be a minus. Well, that's just equal to 1 plus 1, which is just equal to, you guessed it, 3. So that's how we attack a problem of this nature. When we have a polynomial like this, and we have these individual terms through summation, just pass the integral to each term and evaluate individually. Now, you do not have to do it this way. You don't. You can just go straight from here to something like this. You do not have to break it up into each individual one. You can do that. This is just a way I do the problems because I like to break it into each individual piece and attack it from there. But if you don't need to do this, and you don't mind jumping straight to something like this, then you go for it. It'll get you the same answer every time. All right? So that's how we attack polynomials. It's just going to be the power rule, and then that's pretty much it. Polynomials are just power rules, and then be careful when you plug in those limits, because when it's 0 and 1, it's pretty easy. But if it's 1 and 2, 2 and 6, got to be a little careful. All right? So that's it for that example. All right, for this example, it looks pretty similar to that first example we did, except the problem is now is we had this square root in here we have to deal with. So let's tackle this. So we can rewrite this square root as an exponent, which you should always do. If you don't, then you have to memorize a lot of rules to do with square roots, and that just gets tedious. So this becomes 1 over 2x to the 1/2 dx, but when you have an x in the denominator, if you want to put up in the numerator, all you have to do is make it a negative exponent, because the negative exponent means take the reciprocal. So we can rewrite this even further as the integral of x to the negative 1/2 over 2 dx. Now, because I just prefer doing it this way, I'm going to pull that 1/2 out in front. By the way, this process remains the exact same even if you don't do that, just personal preference. And we still have that x to the negative 1/2 dx. So now we have the integral of x raised to some power with respect to x. Now we just do the power rule. So this is equal to 1/2 times x to the negative 1/2 plus 1 over negative 1/2 plus 1, evaluated from 1 to 4. Well, that's equal to 1/2 times x to the 1/2 over 1/2. Well, this 1/2 and that 1/2 are just going to cancel out with each other. So I'm just going to cancel those. That's equal to x to the 1/2 from 1 to 4. Now that's our antiderivative, x to the 1/2. All we did was we pull the constant out in front, rewrite that square root of x, or that 1 over the square root of x as a fractional exponent, do the power rule, and now we are left with the square root of x from 1 to 4. And all that's left now is to do the fundamental theorem step, where we take the two limit points, 1 and 4, plug them into the antiderivative, take their difference, and we get our answer. So this is equal to the square root of 4 minus the square root of 1. Well, that's just equal to 2 minus 1, which is just equal to 1. Now, you might be asking, well, why is it just 2 and not negative 2? Well, that's because when you're integrating, you're ending up with another function. The square root of x here is not just a formula, it's a function. And a function has to pass the vertical line test, meaning each input can only have one output. So if we pass in 4 and I can do plus or minus 2, it's no longer a function. Hence, we only have positive 2 as an output for this function, and we get our result. So that's it for that example. Okay, now it's time for another example. So, we've been asked to evaluate the integral from 0 to 1 of 1 over 1 plus x squared dx. Now this one, there is no tricks. There is no technique you need to use. This one comes from straight memorization. This one comes from recognizing that the derivative with respect to x of tan inverse of x is equal to 1 over 1 plus x squared. There is no other way around this. There is no u substitution you can use, no power rule, no logarithm rule. It is just straight memorization. You have to remember that the derivative of tan inverse of x is equal to 1 over 1 plus x squared. That's the only thing you can do for this problem, which is why I suggest strongly that you have all those derivative rules memorized before taking any exam involving definite integration. So this integral from 0 to 1 of 1 over 1 plus x squared dx, that's just equal to arctan inverse of x from 0 to 1. But another way of writing arctan is as tan inverse of x from 0 to 1. Arctan and tan inverse are the same thing. They're not equivalent, they're the same thing. It's just different nomenclature for doing this, because some people don't like to put this -1 right here because people get confused whether or not this means a reciprocal and inverse. So that's why they went with arctan, and you do the same thing for all the trig functions. So if I use arctan or tan inverse, they mean the same thing. So we got the antiderivative 1 plus 1. 1 over 1 plus x squared is tan inverse of x. And then since we've been asked to evaluate it 0 and 1, that's what we're going to do. So we take that top end point, we pass it into tan inverse. So we get tan inverse of 1 minus tan inverse of 0. Well, this is just equal to pi over 4 minus 0, because tan inverse of 0 is 0. So our answer is pi over 4. Now, right now, you might be asking, how on earth did he get tan inverse of 1 is equal to pi over 4? If he did, don't worry, because that's what we're going to go over right now. We're going to go over how to find tan inverse of 1. So, if we want to do this, we have to ask ourselves a question. First, or I guess two questions. First, what is tan inverse of x? Well, if we recall, tan of x, not the inverse, just the trig function, tan of x. Tangent takes in an angle and returns a ratio of sides. Specifically, it returns the ratio of sides of the opposite side divided by the adjacent side. So what the inverse trig function does is it takes in that same ratio of sides and it returns an angle. So that's what it's doing. This one right here, that's a ratio of sides. What that is telling us is the length of the opposite side is equal to the length of the adjacent side. And so that kind of train of thought leads us to the basically ultimate question on this problem. What angle x gives us tan of x equal to 1? Essentially, what angle, when I pass in a tangent, is it equal to 1? Here's how we go about solving this. So, we want to solve for x. So let's set up our equation. We know tan inverse of 1 is equal to x. So what we can do is take tangent of both sides. But since tan and tan inverse are inherently inverses of each other, so that means tan of tan inverse of 1 is just 1, which is equal to tan of x, since I took tangent of both sides. But what is tangent? Well, tangent is just sine of x divided by cosine of x. Now, since we have this fraction, what I want to do is move cosine to the other side. So multiply both sides by cosine, and we get cosine of x is equal to sine of x. And when we're doing this problem, we want to restrict our mindset to the first quadrant. Why do we want to restrict ourselves to the first quadrant? Because if we expand our domain to all the unit circle, well, then you get a bunch of repeat answers, and that becomes kind of a hassle to deal with. So we're just going to restrict our mindset to the first quadrant and ask ourselves, where in the first quadrant is cosine of x equal to sine of x? Well, here's a hint. cosine of pi over 4 is equal to root 2 over 2, and sine of pi over 4. What just happened? Well, that's interesting. So sine of pi over 4 is also equal to root 2 over 2. So we conclude that cosine of pi over 2, or pi over 4, that was the worst 4 in the history of mankind. Cosine of pi over 4 is equal to sine of pi over 4, which is equal to root 2 over 2. So x equals pi over 4 does the job. Hence, tan inverse of 1 is equal to pi over 4. There's a couple tricks to this one, but probably the most important part of this problem is this: knowing unit circle values. You're going to need to know unit circle values for the gateway. I promise you that. You're going to need to memorize those. That's why I've been saying this all semester. The unit circle values aren't going anywhere. And it's not just for this class. Any advanced math class you take is going to have unit circle values. That I can promise you. There is no escaping them. I know when you left trigonometry or pre-cal, whatever class you did before this, you're thinking, yes, I'm finally done with that. Wrong. It's all over the place. So this is the technique or the process we use to evaluate tan inverse of 1. Why did we want to evaluate tan inverse of 1? Because in this problem, we were required to do so. And something like this has been known to show up on gateways. So I strongly suggest understanding how to do this. Knowing how to calculate tan inverse of 1, or potentially another trig function evaluated at 1 or something like that. You also need to know how to evaluate the trig functions on the unit circle values. So not just calculating the inverses, but calculating the trig values as well. It is very important and a very, very powerful tool to have in your belt. All right? All right. So that's it for that example. All right. Now it's time to evaluate the definite integral from -1 to 1 of the absolute value of x. This one, the big punchline of this one is recalling that the absolute value of x is defined to be the function x when x is greater than or equal to 0, and negative x if x is less than 0. Now, we're just going to use the properties of x, or of the absolute value and the integral, to break this integral up and then evaluate it piece by piece. Here's what I mean by that. So the integral -1 to 1 of the absolute value of x dx, well, this is equal to the integral from -1 to 0 of the absolute value of x dx plus the integral from 0 to 1 of the absolute value of x dx. So all I did was I broke the absolute value function, this integral, up into two portions: the negative part of the integral and the positive part of the integral. Why did I do that? Because on the interval -1 to 0, this is how the absolute value function behaves. It behaves like the function -x. So I can replace this with the integral from -1 to 0 of -x dx plus the integral from 0 to 1 of x dx, because the absolute value on the positive numbers behaves just like the function x. So we broke this integral up into two different pieces where we could actually write down its exact behavior on those pieces. And now it's two basic applications of the power rule. So this is equal to negative of x squared over 2 from -1 to 0 plus x squared over 2 from 0 to 1, because x squared over 2 is the antiderivative of x, and the negative x squared over 2 is the antiderivative for -x. So this gives us the antiderivatives. But now we have to do the fundamental step, the actual evaluation of the definite integral, where we plug in each endpoint and take the difference. So this is equal to -0 minus -1 squared over 2 plus 1 squared over 2 minus 0. Well, that's just equal to 1/2 plus 1/2, which is just equal to 1. And that's how we would go about solving a problem with the absolute values. Now it's time for another example. Let's do the integral from 0 to 1 of x over 1 plus x squared. Okay, now I know this one looks like arctan, but the problem is arctan requires this to be a 1. But we don't have a 1 here. We just have an x. So it is clearly not arctan. We have to do something else. And so this leads us into the first u substitution problem of the day. So let's use u substitution, the technique we learned in the last section, 5.5, to evaluate this definite integral. So let u equal 1 plus x squared. Then du is equal to 2x dx. Excellent. So now we have a u and we have a du. Now let's actually sub these values in. So this goes from the integral from 0 to 1 of x dx over u. But the thing is, I have an x dx in the numerator and a u in the denominator. I don't want to be evaluating this integral with respect to x. I need to be evaluating it with respect to u. So I have to figure out a way to get this du inside this integral. This is how we're going to do it. Because du is equal to 2x dx. Now if you look here, I have my x and I have my dx, but I'm missing a 2. So here's what I can do. I'm actually just going to stick a 2 in right there. Yay. Now I have my 2x dx, which is equal to my du, and we're home free. But there is one hiccup. I can't just plug 2 in willy-nilly. If I do it to one side, I have to counter it on the other. So I multiply 2 here. I have to multiply by 1/2 out in front. Now all I've done is multiply by 1. I haven't changed nothing. So from here, this is equal to 1/2 the integral from u of 0 to u of 1 of du over u. Now why did I do this? Why did I have the limits of integration become u of 0 to u of 1? Well, that's because I changed variables. Initially, I was in terms of x, and my limits of integration were in terms of x. But the thing is, I shifted it. I shifted x and turned it into u. So these limits of integration can no longer be 0 and 1. What we have to do is we have to adjust it accordingly. So what we do is we take these endpoints and we actually plug them in right here. Actually plug them in, because that's what we're doing. We're shifting x and turning it into u. So we take 0 and 1, we plug it in here, and that'll give us our new limits of integration. So from here, this is equal to 1/2 the integral, but u0 is just 1 plus 0 squared, which is just 1, and then u of 1 is 1 plus 1 squared, which is just 2 of du over u. And now we can actually integrate this thing. Well, 1/2 the integral of 1 to 2 of du over u is equal to 1/2 the integral from 1 to 2 of 1 over u du, which is 1/2 times the natural log of the absolute value of u from 1 to 2, which is equal to 1/2 times the natural log of 2 minus the natural log of 1, which is equal to 1/2 times the natural log of 2 minus 0, because the natural log of 1 is 0. So this is equal to 1/2 the natural log of 2. Now you might be asking, why did we evaluate the natural log of 1 but not the natural log of 2? Well, that's because the natural log of 1 is a nice value. It's equal to 0. That's easy. Natural log of e is easy. That's equal to 1. Pretty much the natural log of e raised to any power is easy. Natural log of 2? Yeah, that's not fun. That's not a fun thing to calculate. So we're just going to leave that at the natural log of 2. So what we did here, we set u equal to 1 plus x squared, calculated the du, introduced new variables into our integral, and converted it from a function of x dx to a function of u du. But because we did that, we had to adjust our limits of integration accordingly. And so the limits of integration went from 0 to 1. They became 1 to 2. We got that by just plugging it into this function, u of x is equal to 1 plus x squared. Voila, appropriately shifted our limits of integration. And then we just used the logarithm rule, implemented the fundamental theorem of calculus, canceled some terms, and then we end up with our answer. So that's how we go about solving a problem like this. All right, let's try another example. This one's a little bit easier than that last one. To evaluate the integral from 0 to pi over 2 of cosine of x dx. Well, this one, no tricks. No power rule, no u substitution. This one is straight up just anti-differentiation, recognizing a relationship between a function and its antiderivative. So, this integral from 0 to pi over 2 of cosine of x is just equal to sine of x evaluated at 0 and pi over 2. This comes from the fact that the derivative with respect to x of sine of x is equal to cosine of x. And now from here, now it's the fundamental theorem of calculus time. We just take these two endpoints, plug them into our antiderivative, take their difference. So we get this is equal to sine of pi over 2 minus sine of 0. But what is sine of pi over 2? Well, that's just equal to 1. What is sine of 0? Well, that's just equal to 0. So our answer is equal to 1. So from here, all you had to know was the derivative sine as cosine and then a couple unit circle values. Once again, cannot emphasize this enough. Unit circle values will show up on your gateway. They will show up on your final. That I can promise you. So make sure you know your unit circles for these values. Quick recap. Integrate from 0 to pi over 2 of cosine of x. Recognize sine of x is the antiderivative of cosine of x. And then do the fundamental theorem of calculus at 0 and pi over 2. Calculate this difference. And we get our answer is equal to 1. So that's it for that example. And let's move on to another one. Alrighty, let's do this example. The integral from 0 to 1 of 3x squared times e to the x cubed dx. So, as pointed out in the last lecture, when we have something where we have e to the f of x involved, one of the reasons we like differentiating that is because the derivative of e to the function of x is just e to that function of x times the derivative of that function. It's a very nice property. It's a very nice rule that allows for a quick, easy computation of this. Going backwards is the hard part. That's the hard part. We have to go from here back to here without knowing if this piece right here is actually the derivative. So this is where u substitution comes into play. When you have something like this, when you have a function times e to another function, 80-90% of the time, your go-to should be letting u equal to the function in the exponent of e. Like 80% of the time, that's what you're going to want to do. Set u equal to that function. When we do that here, we get u is equal to x cubed. So du is equal to 3x squared dx. What do you know? You can already tell this is going to work out nicely. Okay, so from here, we're going to rewrite our initial integral, 0 to 1 of 3x squared times e to the x cubed dx. This is going to be equal to, now, since we're about to change our variables, we need to change our limits of integration. So, since 0 and 1 here are in terms of x, we need new ones that are in terms of u. So this lower limit of integration is going to be u of 0. Upper one is going to be u of 1, which is telling us we need to shift 0 and 1 by whatever this function dictates us to do. And now we're going to sub some things in. Well, we made x cubed equal to u, so this is e to the u times 3x squared dx. But what is 3x squared? Well, that's just du that we calculated right here. So this is equal to, now to calculate u of 0 and u of 1, well, we take u of 0, we plug it in, but 0 cubed is just going to be 0. Take 1, we plug it in, it's going to be 1 cubed. Oh, what do you know? It's still 0 and 1. Do not bank on that. That is not always the case. In fact, a lot of the times it won't be the case that the limits of integration remain the same. So make sure you're careful with that. So our quote-unquote new limits of integration are 0 and 1 of e to the u times du. And this is where the beauty of EU comes into play, because the integral of e to the u is just e to the u. But since we're doing a definite integral, we have to deal with these limits of integration from 0 to 1. And now we just plug in e to the 1 minus e to the 0. And that's just going to be e minus 1. Why is it e minus 1? Because anything raised to the 0th power is just going to be equal to 1. So, quick recap. We saw that this was something times e to something else. We set u to be this function in the exponent, calculated du, and then we just went about subbing out everything. We subbed out the limits of integration for our new ones, which were in terms of u. Replace this function right here with u, because that's what we set u equal to. And then we replace 3x squared dx with du. And then just straight anti-differentiation from there. The integral of e to the u is equal to e to the u, because the derivative of e to the u is e to the u. Beautiful property of that. It's absolutely beautiful. And then we just have to finally do that fundamental theorem step where we plug in the two endpoints, take their difference, and we end up with our answer. So that is the strategy of how we want to attack these exponential functions. All right, let's move on to another example. Since we dealt with the exponential function on this problem, it only seems polite to deal with the natural log on this problem because they're related to each other. Alrighty, so here we have the definite integral from 1 to e of 2 times the natural log of x divided by x with respect to x. A lot of x right there. Alright, usually when we see a problem like this and we have some function here in the denominator, we usually want to set u equal to the denominator. This is not the case here, because if you let u equal to x, then du is equal to dx, and all you've done is replace all these x's with u's. You've gone nowhere. That is literally no help whatsoever, unless for some reason you just prefer the letter u to x, in which case, go for it. But in terms of actually solving the problem, it's not really helpful. So we got to come up with something else. Well, right here, that's just a constant. Constants are never helpful for us. They really aren't. They're just annoying. They're consistently annoying. Now, all that leaves us with is the natural log of x. So let's just give that a try. Let u equal the natural log of x. Then du is just 1 over x dx. What do you know? We have a 1 over x dx buried in here. So we got to go pull that guy out. So the integral of 1 to e of 2 the natural log of x over x dx is equal to 2 times the integral from 1 to e of u over x dx, right? But we have a 1 over x right here times dx. Sorry, getting a little ahead of myself. 1 over x dx. But 1 over x dx is simply du. So this is equal to 2 times the integral of u du. Except we are missing our limit of integration. But since this function's in terms of x, these limits of integration are in terms of x, so we have to shift these limits of integration using u. So our new limits of integration are the natural log of 1 and the natural log of e. This is just equal to 2 times the integral of natural log of 1 is just 0, and the natural log of e is 1. Those are a couple things you're just going to have memorized. Lock down the natural log of 1 is equal to 0, natural log of e is 1. Just know that. That's something you're going to want to know. Of u du. Well, here, since we have a function in terms of u, we're integrating with respect to u. It's just doing the straight power rule here. So we have 2 times u to the 1 plus 1 over 1 plus 1 evaluated from 0 to 1, which is equal to 2 times u squared over 2 from 0 to 1. But let's just go ahead and cancel out those 2's. So it's u squared from 0 to 1, which is equal to 1 squared minus 0 squared, which is just equal to, you guessed it, 1. So what we did here is we initially tried setting u equal to the denominator, quickly ruled out that as a possibility for working. So we set u equal to the other function, the natural log of x, calculated du, did the appropriate substitutions, and since we changed variables, we have to change the limits of integration. I cannot stress that enough. You have to shift the limits of integration if you're going to keep it in terms of u. If you're going to get to this step and plug in, if you get right here and you plug in 1 and e, you're going to get the wrong answer. You're going to get e squared minus 1. And the last time I checked, e squared minus 1 was not equal to 1. I think e squared minus 1, what is it? Yeah, that's a problem for another time. I'll bore with you guys that later. So, if you're going to do this step, you're going to evaluate it in terms of u. You have to change your limits of integration. You plug in 1 and e, you're going to get the wrong answer. So, when attacking a problem like this, this is the strategy you want to use. All right. Now, you guessed it. Let's try another example here, shall we? All right. So this situation. The integral from 0 to 0.5 of 2 divided by 1 plus 4x squared dx. All right. When you see a function like this, 70% of the time what you're just going to do is let u equal to the denominator, which in this case is 1 plus 4x squared. Like 70% of the time, that's what you want to do. If you're not entirely sure where to start, just set u equal to the denominator and go from there. So u is equal to 1 plus 4x squared. So du is equal to 8x. All right, cool. All right, so where do we want to go from here? All right. So let's go ahead and pull that constant out in front because, you know, they bother me. So we have 2 times the integral from 0 to 1/2 of 1 over u dx. All right, cool. But now the thing is this requires an 8x dx. We do not have an 8x dx there. So we have to introduce an 8x. How do we do that? Well, multiply by a clever choice of 1. So this is equal to 2 times the integral from 0 to 1/2 of 1 over u times 8x over 8x dx. Well, this is just equal to 2 times the integral from 0 to 1/2 of 1 over u times du over 8x, because 8x dx right here is just equal to du. So we boil this integral down to 2 times the integral from 0 to 1/2 of 1 over u times du over 8x. Anyone see a problem with that? Oh wait, that's right. I'm in my bedroom by myself. There's no one here to answer that question. All right, so I guess I'll have to answer it. The problem with this is this x right here. We have a du. We have a u, but we're still stuck with an 8x. What do we do? Well, this is what we call a problem, because when we did our u substitution, we got it in terms of 1 over u. We got a du in there, but we're still stuck with an 8x in there that there is nothing we can do about. There's nothing we can do about it. We can try and solve for x in here and then try and sub it back in, but that's just going to get way ugly. So the problem here is we chose the wrong u. If we set u equal to the denominator, we run into a very big problem right here, that there is no way around it in this situation. But that doesn't mean this problem's impossible. All it means is my choice of u was wrong. As like I've said before, you build up intuition on what u to choose. Sometimes you're going to choose the wrong one. Half the battle is trying to just pick what u you want to use. And another good portion of it is recognizing when did it go wrong. Because if you go here, you can spend another 5 minutes trying to finagle this into working. But when you get to here, it's just obvious that this just is not going to work anymore. We need a different choice of u. So what I want you to do is, before you see us work the correct use choice, play with this problem a few minutes. Take some time. Take 10, 15 minutes. Try and see if you can figure out what we should use. All right, and that's where we're going to pick up in the second part of this video lecture.